Hi. I want now to draw your memory back to a demonstration I did a few recordings ago where I showed you up on the desktop a light bulb connected to a capacitor connected to a battery. And when I did that, when I first connected it and the capacitor was initially uncharged, the light bulb lit. It was initially very bright, but then it got dimmer and dimmer and dimmer and finally went out. And then after that, I disconnected the battery and then connected the light bulb to only the now charged capacitor. And again, the light bulb lit and dimmed and went out in exactly the same way as it had when it was connected to the battery and as well as the capacitor. And we're still not quite at the place where I can fully explain what happened, but that's where we're heading right now. And of course, we're going to pick up a number of other important topics along the way. So I'm going to draw a schematic diagram of that situation here, and I want to talk about a couple of things. So here's a wire, and then we come down here, and there is our light bulb, and connected to the other side of the capacitor. So obviously this is the second part that I discussed where the capacitor had become charged after we had had it connected to the battery. So this is part two, no battery, just a charged capacitor. We connect it, and as you know, the light bulb lights. Okay. As I say, I'm not yet going to discuss the why of the bulb behaving as it did, but as I say, we're heading there. But I do want to point out something new that has happened. That I snuck it in on you, and I didn't actually motivate it or say it was okay or anything. I just said that it was going to happen, and I trusted you to either overlook it or to trust me that it was okay. But let's come back to it. Let's take a step back. The issue that I have in mind here is the idea of our charges moving. We haven't done that before. We've had source charges. They create electric fields or they create electric potential differences or whatever it is they do, but they've always stayed where we put them. But now I sneakily snuck in on you that our charges may move. We haven't seen that before, and that brings in some new issues. And so I want to start discussing that a bit. Okay, so let's see what happens. Another thing I want to remind you of is the assumption that we are making that when charges move, when a current flows, the things that are moving are positive charges. We know better. It turns out that it's actually the negative electrons that are moving, but because reasons, I'm going to assume that it's positive charges, and I'll explain that, eventually, someday, sometime. Okay, so that assumption made, then when the capacitor discharges, the excess positive charges on this top plate here will be attracted to the negative plates on the bottom of the capacitor, but of course they can't jump this gap. There's either vacuum in between them or there's a dielectric material in between them. In my schematic diagrams, by the way, I'm never going to draw the dielectric. If it's there, it's there. If it's not, it's not. I don't need it in my diagram. But whatever is in between these two plates, it's going to prevent any charges from jumping directly across the gap from the one plate to the other plate. So these positive charges can only get to the negative plate by passing through the light bulb. Okay? And when that happens, the charges flow through the wire, eventually populate themselves on the bottom plate. The top plate becomes less and less positive, the bottom plate becomes less and less negative, and eventually an equilibrium is reached where both plates have the same net charge, namely 0. The capacitor is now said to be discharged, but I'm going to focus on this idea of the moving charges, these charges moving through the wire. So the charges move this way, go this way. They're forced to go through the light bulb because it's in their way. We say that it's wired in series with the capacitor. The current flows through the light bulb, comes out, comes this way, goes up, lands on the bottom plate, and there we are. Along the way, a couple of things happen. First of all, this flow of charge has a name, and we call it a current. You've doubtless heard this term before. We have an electric current. The symbol that we give electric current, I don't want to give it the symbol E for electric because we're using E for electric field. I don't want to give it C for current. We're using that for capacitance and for coulombs for that matter. So moving charges, since they're moving, I don't want to call them just Q because Q by itself just means charge, doesn't say whether they're moving or not. So anyway, the symbol that got chosen was the symbol, the letter I, either uppercase or lowercase. My personal choice is always use capital I. Your book may be using lowercase I, or it may use both. Doesn't really matter that much. Kind of the same deal with capital Q and lowercase q for charge. Okay. In any case, I'm going to use capital I. There is a relationship, obviously, between the current and the charge, and I will explicate that later. But anyway, so what we say is that we have a current that flows through, and it turns through the entire circuit, and it turns out that this current, the flow of charge is identical at every location within the circuit. Now it changes with time, but it's the same at every place within the circuit. So the current here is the same as the current here, is the same as the current here. Okay. Now there is no current across the capacitor plates, but that's all right. I'm just trying to light a light bulb. The other thing that happens is, well, I light the light bulb. Okay? And along with anything else that is true, since the light bulb gives off light, it's emitting energy. And especially what are known as incandescent light bulbs, if you happen to remember what those are, the old-fashioned kind that got really, really hot. Well, they got really, really hot, and that's a form of energy as well. So the light bulb is giving off at least two kinds of energy. But conservation of energy, where does that energy come from? Okay, we're going to discuss that, but I bet you can guess what the answer is. Remember, there's a potential difference across the plates. The potential difference acting on the charges on the plates gives the charges electric potential energy, and then so as the current flows, something happens when the charges pass through the light bulb that causes them to give up some of their potential energy, and that potential energy gets converted to other kinds of energy, such as I say, light energy or thermal energy, or perhaps some other kinds. Okay, and another thing that will happen, which we're not going to be anywhere close to talking about now, right now, but we will get to eventually. But I thought since we're here, I'll go ahead and mention it. A new thing happens when the charges move that doesn't happen when they don't move, and that is along with the current, along with the energy transfers, along with whatever else happens here. A collection of moving charges that it's an electric current also generates what's known as a magnetic field. Along with the electric field, it generates a magnetic field. What's a magnetic field? We'll study it later. But the magnetic field occurs and exists only for moving charges, never for motionless charges. Okay, so that's some ideas and some mysteries for setup. And what I'm going to do in the next recording is talk in more detail about the current, what's going on there, what causes the current to happen, what tends to interfere with the current happening, and maybe even explain why in the world we're assuming positive charges doing the moving, even though we know that's not true. Okay, that'll be later. Next.